Okay.
Sure.
All right.
All right.
So now,
Yeah.
now we're recording. So I'm going to mute my microphone since I'm in a sort of public space and you can hear people going on. So, Melvin, go ahead with your talk.
Sure. Yeah. Well, so thank you for giving me the opportunity to speak. I'm Melvin Leok. I'm a professor of mathematics, and I guess I'm a combination of an applied and computational mathematician. And I'll be talking about some of the stuff I've been working on. Primarily, it's like illustrated by a bunch of videos, just to give a sense as to, what applications this work, it's like could be applied to. And the title of my talk is Computational Geometric Mechanics and has been very generously funded by the National Science Foundation and the Air Force. So let me start by giving you a sense as to where geometry might show up. It's like in interesting ways. And the first of this is, say, if you have a falling cat, and if you drop a cat, it's like with its legs pointing upwards, and what you see is that the cat bends its body and twists. And because of that, it's able to rotate itself, even though there's no direct actuation of the rotational dynamics of it. And that more or less has to do with a coupling between the shape dynamics, it's like in the rotational dynamics, through the conservation of angular momentum. And so the condition that you are at zero angular momentum, it's like induces what is known as a connection. It's like on this space, and that turns out to have interesting applications in control. So perhaps an easier way to visualize this is that the cat rotating, it's like in space, is an example of what is called a geometric phase, which is basically an example of holonomy. And holonomy is basically what happens if, for example, you have a tangent vector, it's like on the surface of the sphere, and you just parallel transport it around this spherical triangle. So you can do this with your hand. It's like you stick your thumb up and you just sort of sweep your hand around. It's like then the natural motion of this will cause your thumb to go from here, it's like to here. And the amount by which your thumb rotates turns out to be related to the amount of curvature which is enclosed in this loop. And so there's this nice video here, it's like which illustrates that same concept. There's a frame on the sphere, it's like, and as you rotate, it's like around the spherical triangle via parallel transport of that frame rotates. Okay. So you might ask, well, what's the relationship between, it's like this notion of curvature and the cat? And the basic idea is that the cat's moving around in some abstract shape space and comes back to its original shape. And as it does this, that's analogous to moving, it's like on the surface of the sphere. The shape motion is analogous to the surface of the sphere. And then its orientation is analogous to this tangent vector. And so it's like as you move around in shape space, you end up rotating. Okay, and it's because it's like there's a precise sense in which the space of zero angular momentum is curved. So other examples of this kind of holonomies are, if you have, for example, a spiral staircase and you're moving in a way which such that the projected motion on the XY plane, it's like there's a circle, but you're constrained to be on the spiral staircase. And as a consequence of that, your total motion involves a translation in the Z direction as well. So that's another simple example of this. And that can be applied to things like control of satellites. So this is the Hubble Space Telescope, and you can control the orientation, it's like of the Hubble Space Telescope using internal momentum wheels. And the advantage of these kind of geometric phase type controls is that the moment you stop these, it's like sort of reaction wheels, as they're called, the satellite stops rotating. So if you were to directly actuate the rotational dynamics, it's like of the satellite via thrusters and applying a torque to the satellite, then obviously it will stop rotating. But it's very, very difficult then to cancel that rotation out exactly so that it ends up being stationary because the thrusters are not really that precise and there's no dissipation in space. So these type of geometric phase controllers, it's like are preferable for attitude control, it's like of satellites for that reason. So this is another simple illustration of this. You have this cuboid that's like with reaction wheels, it's like around them which rotate, and the moment they stop rotating, it's like you'll see that the satellite or the cuboid stops rotating as well. Okay, similar things happen. It's like in biology. So if you have a paramecium, for example, it's like, or you have spermazoa, it's like, then, it's like anytime you have sort of small objects, it's like in fluids, you end up having a situation where you're in a low Reynolds number flow. So the fluid is, in some sense, very viscous or very laminar. And in those situations, propulsion tends to be of this kind of geometric phase like nature. Okay. And so that's one example where these kind of geometric phases might show up. It's like in biological applications. Okay, so what I primarily work on is the construction of numerical methods which preserve geometric structure. So let me give you some examples of what one might mean. It's like by preserving geometric structure. So invariance of a dynamical system might include things like the energy. There may be certain symmetries and invariance properties. It's like of the system themselves. It's like there may be some sort of reversibility or monotonicity condition. A lot of times associated with symmetries are sort of momentum conservation laws, like true Noether's theorem, because if you have say a Lagrangian Hamiltonian system which is rotationally invariant, then the angular momentum is conserved. If you have something which is translationally invariant, the linear momentum is conserved. If you have a fluid system, it's like, and there's what is called the particle relabeling symmetry, and that turns out to be associated with what is known as the Kelvin circulation theorem, which says that if you take a loop in the fluid and you advect that by the fluid flow, then that advected material loop sort of encompasses, it's like a circulation which is constant. So again, if you have a Lagrangian Hamiltonian system, then there's what is known as a symplectic form, which is preserved. And if you're looking at simple systems, a lot of times there's this notion of integrability. And you might ask whether or not you can construct discretizations with respect to those geometric properties. So the reason why, it's like one wants to think of them as geometric properties, which are, and why they're important, is because these geometric objects are invariant in some sense, then you know that the dynamics is restricted to a level set, it's like of the geometric invariant. And that can oftentimes result in very severe constraints on the ways it's like in which the dynamical system it's like can evolve. And so if you have a numerical method, it's like which respects that, it's like then there's a sort of rigidity which means that from a qualitative perspective, the numerical solutions you get tend to be much better behaved. Okay, so other times the equations themselves live on a manifold, for example, the space of rotations. And you might ask, how do you go about constructing numerical methods which make sense on a manifold instead? And the reason why that's important is because many numerical methods, particularly for the solution of differential equations, assume some sort of linear space structure. So, it's like, so for example, with the Euler method, you take the solution at the old time, you add h times the vector field at the old time, and that gives you an approximation of the solution at new time. But because of the fact that you have this addition operation, that sort of assumes that you're working in a vector space. And so if you're actually working on a curved manifold, then you have to ask yourself, how do you generalize those type of simple generators of flows, if you will, in order to construct computable numerical methods. So as I sort of alluded to, the main goal of what is called geometric integration then is structure preservation. And the net effect of structure preservation oftentimes is that it allows you to better reproduce long time properties. So the way this shows up is that you have discrete conservation laws, and the sort of structure preserving algorithm which you have conserves a discrete quantity, it's like which is always close to this continuous quantity you're actually interested in. And so from the point of view of level sets of these invariants, you stay sort of closed for a very, very long time. So maybe a better way to illustrate this is the following cartoon. So if you have, say, this green line, which is the sort of energy level set, it's like of the continuous or the real energy, and you have some sort of perturbed or discrete energy, which is exactly preserved, then you'll stay on this sort of level set of this perturbed energy. And it's usually the case that the level set of the perturbed energy stays close to the level set of the original energy. And so you have some sort of stability as a consequence of this. So let me try to illustrate these ideas. It's like with some simple examples of numerical methods. The easiest one is probably the Ford-Euler method, which has the form which I talked about, that the solution at the new time is equal to the solution at the old time plus h times the vector field at the old time. Inverse Euler is sort of similar, except that the vector field is evaluated at the end time. And symplectic Euler is this kind of strange thing where you have the vector field, but it's evaluated the initial position by the final momentum, which seems a little bit counterintuitive, but it has sort of some nice properties, which we'll see in a little bit. Okay, so anyway, so you can apply, it's like the Ford-Euler method to the solar system. And when you do this, it's like you'll see that it doesn't really bode well for us. It's, it's sort of one of those planets that's like got voted out of the solar system. And so, and if you look at it from the energy point of view, it's like, it's like the energy error sort of grows. It's like quite significantly, it's like over something like 200 years, right? So this is not to say that the solar system is it's like non-chaotic, but over 200 sort of year time scale, it's like it is fairly deterministic and doesn't do anything too dramatic. So this is a little bit disturbing that the numerics does this to you. So you might think, well, maybe it's because your numerical method is unstable. So if you know something about numerical methods, it's like then you know that the backward Euler method or the inverse Euler method is unconditionally stable. And if you run this, it's like then you'll see that you still end up in a situation where one of the planets gets voted out of the solar system. The energy does quite well for a little while. It's like, and then it sort of just bounces up. And this really is due to a combination of factors, one of which is that inverse Euler is dissipative in some sense. So it contracts phase space. And then once you get close enough, it's like to the central, it's like mass here, it's like round off error causes you to sort of have this kind of large ejection. Okay, so anyway, so instead you can look at what happens with symplectic Euler, which is this kind of strange thing where you evaluate the vector field at initial position, final momentum, and you'll see that over a comparable time scale, it's like you have these perfectly nice ellipsoids. And again, as I said, it's like, this is not to say that the solar system is non-chaotic. It's like, but again, over 200 years, you don't really expect anything dramatic to happen. And you see that the energy error there is extremely small. It's basically oscillating about its true value. Okay, so that's quite a dramatic difference. And that's at least in part due to the fact that symplectic Euler is, as the name implies, symplectic, and in particular, it preserves phase space volume. Okay. So most of what I do sort of focuses on this idea of starts, if you will. It's like in the continuous theory, it's like, it's like from the perspective of what is called geometric mechanics. And geometric mechanics involves the use of differential geometry and symmetry techniques to study analytical mechanics, particularly Lagrange and Hamiltonian mechanics. And computational geometric mechanics, it's like aims to use or construct computational algorithms using these ideas. And in particular, it's like a lot of what I work on is based on this idea of variational integrators, which are based on discretizing Hamilton's principle. And they have the advantage that if you construct your integrators in this way, they're automatically symplectic. And under fairly reasonable conditions, they are also oftentimes momentum preserving. So the way you go about doing this is that you start with the continuous Hamilton's principle, which states that if you have an initial and a final point, then the trajectory, it's like which joins those 2 points, is that which extremizes the action integral, which is the integral of kinetic minus potential energy. And you can discretize that by imagining that you replace that curve, it's like by a bunch of sample points, and you replace the action integral by what we call the discrete Lagrangian, which you should think of as a piece of the action integral. And if you sum up those discrete Lagrangians over the sequence of points, you get an approximation of the action integral. And you can require that discrete action sum is stationary with respect to variations of these internal points, subject to keeping the endpoints fixed. And when you do that, you end up getting what is called the discrete Lagrange equations. Okay. So the D2 here just means I'm taking the partial derivative with respect to the second slot, which in this case is just a derivative with respect to Q1. And this D1 is the partial derivative with respect to the first slot, which again is a partial derivative with respect to Q1 here. So you can think of this equation as implicitly defining for you a two-step map. It's like from pairs of points to pairs of points, Q0, Q1 to Q1, Q2, right? And so this allows you to time march the solution forward. Okay, so I won't go too much into the details of those things, but let me just at least say that you can apply these type of methods to multi-body systems. So you'll see some examples of it being applied to the double spherical pendulum, to basically, this is an articulated rigid body in a perfect fluid. It's like where the perfect fluid effects are modeled using added mass effects. And then this is a reeling mechanism. It's like attached to a rigid body. It's like, and there's an elastic cable it's like connecting the two. And the color coding represents the stress in the cable. It's also been applied to biomechanical models. It's like, in particular, it's like models of grasping. It's like for human skeletal systems. And this is due to Todd Murphy. It's like Todd, in fact, has a really nice piece of code which allows you to construct these models by essentially interconnecting simpler models. And so that is going to turn out to be one of the important ways to construct or to systematically construct, complicated models from simpler ones is by what is called interconnection theory. And you can apply this not just to ODEs, but to PDEs as well. It's been used, it's like in continuum mechanics, it's like plasticity, it's like elasticity, it's like, it's like strings with some sort of intrinsic curvature, stuff like this. Okay, so let me go back to, it's like this issue of symplecticity. And in sort of, it's like in 1+1 phase space, symplecticity basically corresponds to volume preservation. Okay, so if you start off with a set of initial conditions and you advect this, it's like by the flow, it's like then you'll find that the volume, it's like enclosed, it's like by this initial set of conditions, it's like stays constant, and the same thing is true even if you have this very dramatic stretching motion. So you can ask what happens when you have a numerical method and you try to do the same thing, it's like to this set of initial conditions. And you see that with explicit Euler, what happens is that you could start off with this phase volume or phase area, and under the flow of the explicit Euler method, it's like that phase area increases. With implicit Euler, it's like it's like that phase area actually decreases or decays, and symplectic Euler, it's like preserves that. So symplectic methods are also automatically volume preserving, right? And again, it's like in this 1+1 case, it's like those are equivalent statements. But I would say that in higher dimensions, that's not equivalent, and that's going to turn out to have interesting implications when you do propagation of probability distributions, which I'll talk about later. Okay, so anyway, so this is just to illustrate that amongst other things, symplecticity, it's like results in volume preservation. And volume preservation, it's like in this sort of low dimensional case is equivalent to symplecticity. All right, so you can also generalize these ideas to construct numerical methods which evolve non-Lie groups. And the way you go about doing this is that you can construct the following ansatz, which more or less says that the curve, it's like on the Lie group is the exponential of some curve in the Lie algebra times the initial point in the Lie group. So to make this more concrete, if, for example, you have the space, if your Lie group is the space of rotation matrices, then its associated Lie algebra is the space of skew-symmetric matrices. And you can use the matrix exponential to map skew-symmetric matrices to rotation matrices. And if you multiply rotation matrices, you again get rotation matrices. So the way it's like this sort of ansatz imposes is like the condition that you have dynamics on the group is by exploiting the fact that the group is closed under the sort of multiplication operation, and that the exponential map maps the Lie algebra to the Lie group. Okay. Now, the reason why it's nice to rewrite this curve in time, it's like in terms of this curve on the Lie algebra, is that the Lie algebra is always a linear space. So again, the Lie algebra associated with the space of rotations is the space of skew-symmetric matrices. If you add skew-symmetric matrices together, you stay in the space of skew-symmetric matrices. So you can use all the standard linear approximation techniques you might want here. You can take linear combinations of basis functions in the space of skew-symmetric matrices, and then, it's like use that to construct now a curve which lives on the Lie group. Okay, so with that ansatz, you can plug that into the discrete variational principle, and then you can construct a method which automatically stays in the group. So as I said, you can apply this to, it's like articulated rigid bodies. This is a set of 3 rigid bodies, it's like which are articulated with 2 universal joints in a perfect fluid. And the motivation for this is to try to do models, it's like of things like underwater fish, right? So I got my PhD at Caltech, it's like from the Control Dynamical Systems department. And I used to joke that many of the people who graduated from that program and got faculty positions also got, as part of their startup packages, access to a swimming pool so they could do all this underwater fish thing, which was in the vogue at the time. But one of the problems that's like you see with these carangiform fish is that they're very simple geometrically. Okay, they're basically a single rigid body. It's like with 1 degree of freedom, S1 degree of freedom for the fin. And a big part of that, I think, is that was an easy thing to model mathematically. And so, it's like, I guess one of the take-home messages I wanted to communicate is that there's been a lot of advances in terms of mathematical modeling and numerical analysis is like for dynamics on much more complicated spaces. And I don't think that it's really percolated, it's like to the engineering community, it's like as much as I would like. Okay. All right, so anyway, so you can use sort of a similar articulated rigid body model. It's like to model the following cat. All right, so this is a real cat being dropped in slow motion. And so you can see this, it's like rotation. This thing on the right was an attempt to construct a robot, which does something similar. And this thing in the middle, it's the mathematical model. It's like, and the way I would like for you to interpret this is that if you imagine it's like in this sort of purple or reddish part, it's like there were little legs pointing out, right? And it's the cat that has its legs pointing up, and then it's like at the bottom, it's like the cat has its legs pointing down. So that even that simple mathematical abstraction is enough to capture the essential physics of the problem, and that's what's represented here. It's like in the actual engineering model as well. Okay. So there are other examples of geometric phases. It's like, and they're closely related to this idea of underactuated control. So the falling cat is an example of an underactuated system because it has both rotational and translational dynamics, but you only you're not directly actuating, it's like the rotational part of it. Okay, so this is an example. It's like something similar where you have a heavy top and you can move the center of mass around. It's like, but you can't rotate about the center of mass. And of course, to make things interesting, the goal is to start off with the heavy top in one position, and you want it to rotate by a certain amount. And if you can only control the center of mass of it, in order to do that, you have to do this very large maneuver to pick up the geometric phase in order for it to rotate. Okay. Yeah, anyway. So other examples of these kind of phase-like effects are if you try to parallel park, right? So if you parallel park your car, it's like you can move your car forwards and backwards and you can rotate it. But when you want to parallel park your car, what you really want to do is to move perpendicular, it's like to the wheels. And you can't do that using do this linearly, but you can do this in a nonlinear way by looking at the commutator of the two flows. So if you move your car forward, rotate it left, move your car backward and rotate it right, then if those two flows commuted, then you would get nothing. But the two flows don't commute and you get a motion which is essentially the Lie bracket of this thing, and that has a component which is perpendicular to the wheels. And then this is that underactuated control thing again, and it's just meant to illustrate that what it wants to do optimally is to encompass a region of high curvature, which here is labeled blue. And so if the region of high curvature is far away from where you start off with, then you'll have these very large maneuvers, which are illustrated here. And if your region of high curvature is close to where you start off, then it's not going to make as aggressive a maneuver. So why is that important? That's important because most traditional analytical methods for doing control in this nonlinear setting, it's like involve sort of series expansions, if you will, and in terms of the brackets of the system. And if you are in this region of high curvature, it's like then that kind of local series expansion based method works perfectly well. But if you're in this situation where the curvature is very far, the high curvature region is very far away, then staying close to that using local expansion-based methods, it's going to give you a suboptimal solution. Okay, so other things it's like which we've worked on is this idea of uncertainty propagation, which more or less is a question of if you have a distribution on a curved space, it's advected by some sort of flow. How do you compute the advected flow? Okay, and here it's like this question of symplecticity, it's like rears its head again, because there was a passage from the Bible, it's like about, it's like the camel treading the eye of a needle. And as you probably know, it's like if you take a camel, it's like hypothetically, it's like, and you applied volume preserving transformations to it, then there is a way to tread the eye of the needle. You sort of compress in one direction, but you spread out in another. It's like, and that would allow you to tread through the eye of the needle. But if you were to try to do this with symplectic transformations instead, then it turns out that you can't always do this. And this is a consequence of what is called Gromov's non-squeezing theorem. So it has to be that the sort of essentially the projected area, it's like in a matched position momentum plane, right, is small enough. It's like for you to be able to go through a needle, it's like which is in that, which is aligned in that plane. Okay, so the bottom line then is that, yep, sorry.
Yeah, so I wondered if you're getting to the end of your talk because it's been...
Yeah, I'll finish up soon. Yeah, so so let me just show you some more videos. It's like, and this is just meant to illustrate that you can again do these type of calculations. It's like on curved spaces, and you can put, you can advect probability distribution of curved spaces. Okay, and then these are some other simulations. It's like which we've done. It's like this is double spherical pendulum, and it has the advantage that it's a global formulation. It doesn't require constraints, but it has no coordinate singularities. You can use the same kind of idea to do geometrically elastic rods. You can do sort of magnetic arrays. It's like, so if you're trying to model something, it's like where you have directions, it's like in a fluid, it's like, and they interact, it's like in some way, it's like you can model those things. And then it's like more recently, we've applied this to collision algorithms. So this is just a simulation of a dice, cube, but with slightly different initial conditions. So you'll see that after a little bit, it's like those two initial conditions are going to diverge from each other. And this is just meant to illustrate that, it's like we have collision algorithms which are very, very robust. It's like, and yet able to take into account the fact that very small changes in initial conditions, it's like lead to wildly varying, it's like outcomes after, sufficient collisions. And so this is when they start diverging from each other. Okay, so anyway, so let me go ahead and round off by saying that geometric structure preserving numerical methods respect the geometry and the conservation laws. And so this has an important role. It's like in characterizing the long-time behavior of dynamical systems, and it has implications for control. I should mention that if you want to do adjoint sensitivity analysis, then it turns out that even if you start with a differential equation which is not Hamiltonian or Lagrangian, the adjoint system is Hamiltonian, and so symplectic methods play an important role there. And you can also study this issue of uncertainty quantification and propagation. So one thing I didn't mention, which I think is important, is that you can then take these simple models and you can interconnect them to construct, hierarchical interconnected multi-scale multi-physics models. So the most obvious applications in the context of this collaboration, I think, is to biomechanical systems and possibly nanorobots. It's like in low Reynolds flows. But you can also model sort of complex multi-physics field theories, and you could consider perhaps the advection of complex biomolecules. It's like in sort of in the body. So let me just stop there. Thank you.